Next, we want to compare sets in terms of their sizes. For instance, we might want to say ultimately that a finite set is somehow smaller in size than some infinite set. But there are different ways of comparing sets to this effect. For instance, we might say that sets are subsets of some other sets, like the set consisting of 1 is a subset of the set consisting of the numbers 1, 2, and 1, 2 is a subset of 1, 2, 3. The idea is x is a subset of y if and only if, for all z, if z is a member of x, then z is also a member of y. Indeed, 1, 2 are the only members of 1, 2, the set, and both of them are also members of the set 1, 2, 3. Therefore, the set 1, 2 is a subset of the set 1, 2, 3. On the other hand, the set 1, 2, 3 is not a subset of the set 1, 2, since not every member of 1, 2, 3 is a member of 1, 2. Indeed, 3 is a member of the set 1, 2, 3, but not of the set 1, 2. We can summarize this example by pointing out that the set 1, 2 is actually a proper subset of the set 1, 2, 3. In general terms, x is a proper subset of y if and only if x is a subset of y, but y is not a subset of x. So it holds, for example, that every set is a subset of itself, but no set is a proper subset of itself. All right? We've just compared sets by means of the proper subset relation. Intuitively, in some sense, if a set x is a proper subset of a set y, then x is smaller than y. Now here's another way of comparing sets in terms of size, by pairing off their members. Pairing off means here that there is a way of correlating the members of one set with the members of another set, so that one does not forget about any member of either set, and each member of the one set is correlated with exactly one member of the other. For instance, there is a pairing off between the set 1, 2 and the set Hannes Leitgeb, Stefan Hartmann. This is a different manner of pairing off the members of these sets. On the other hand, there is no way at all of pairing off the members of these two sets, the set 1, 2, and the set consisting of Hannes Leitgeb, Stefan Hartmann and Zeno. However one tries to correlate the members of the one set with the members of the other, some member of the smaller set would have to be correlated with more than one member of the other set, which is not what we mean when we say pairing. Why is there a pairing between 1, 2 and Hannes Leitgeb, Stefan Hartmann? Well, there is none between the set 1, 2 and the set Hannes Leitgeb, Stefan Hartmann, Zeno. Well, because the set 1, 2 and the set Hannes Leitgeb, Stefan Hartmann are of equal size, while Hannes Leitgeb, Stefan Hartmann, Zeno is larger than 1, 2. It has more members. We have introduced two ways of comparing sets with each other. Sets can be subsets, and indeed proper subsets of other sets, and the members of sets can be paired off with members of other sets. We can use either of these concepts in order to get a better grasp when a set has equally many members as another set, and when this is not the case. But we need to be very careful in doing so, or we might end up in paradox again. The first one who actually realized this was Galileo Galilei. Yes, I mean the famous physicist from the 16th and 17th century that you all know about. In a fictitious dialogue, Galileo presented a paradoxical argument about infinite sets. In the following, I present a slight variant of Galileo's original argument. These are the premises. P1. If x is a proper subset of y, then x does not have equally many members as y. This seems plausible if one thinks of our previous example. The set 1, 2 is a proper subset of the set 1, 2, 3. And indeed, 1, 2 does have less members than 1, 2, 3. So the set 1, 2 does not have equally many members as the set 1, 2, 3. Also, the following premise looks just fine. P2. If there is a pairing off between the members of X and the members of Y, then X has equally many members as Y. Just reconsider our previous example. There was this pairing off between the set 1, 2 and the set Hannes Leitgeb, Stefan Hartmann. Once again, the set 1, 2 does in fact have equally many members as the set Hannes Leitgeb, Stefan Hartmann. The next premise is clearly true. P3. The set of even natural numbers is a proper subset of the set of positive natural numbers. That is, the set 2, 4, 6 and so on is a proper subset of the set 1, 2, 3, 4, 5, 6 and so on. After all, every even natural number is also a positive natural number. Where by positive, we mean here simply that we're excluding 0, and that is just for convenience. But also the following is the case. P4. There is a pairing off between the even natural numbers and the positive natural numbers. This can be seen by correlating each even natural number with its half, or the other way around, each positive natural number with its double. But from all of these premises taken together, we may logically conclude, conclusion, the set of even natural numbers does not have equally many members as the set of positive natural numbers, and the set of even natural numbers does have equally many members as the set of positive natural numbers. For by premises 1 and 3, we get that the set of even natural numbers does not have equally many members as the set of natural numbers. And from premises 2 and 4, we can derive that the set of even natural numbers does have equally many members as the set of positive natural numbers. This is a logically valid argument in which each premise is plausible if taken by itself, but the conclusion of which is absurd. In fact, the conclusion is even a logical contradiction. Galileo hit upon a paradox again. Just as in the case of Zeno's paradox before, some premise needs to go. But which one? Or which ones?